said, I'm Stephen Thue, assistant professor here at Computer Science. I'm going to tell you today not just about Conway's game of life, but also about the Turing machine that's Conway's game of life. There we go. Here's a bit of an outline. First outline for what is everyone talking about general intuitive particularly called the game of life. Then do a little bit of working with Turing machines, which are also informed just a quick refresher of a particular one that C implemented in the game of life as proved. But interactive motivation and ego. Every third person in each room needs to stand up. And some of this technique abilities. So there and back. It's okay, I know you can stand these things. Okay, right, okay. Now, everybody count the total number of people standing in one row, and you're calling, you can interpret the columns as you like. Doesn't matter too much. Okay, including yourself. So count the number. Okay, only count the number of people standing. Okay. Okay, when I say go, if the number that you counted was even, or sorry, if it was odd, so count, in this case, if it was even, stand up. If it was zero, well, in this case, you should have to move. But it could happen later. So, okay. Same way to guide. Ready? Go. Okay. Sit down. Alright. Okay, now let's do it one more time. Count again. See how many people are standing here on the column. It's odd, stand. Sure, it's odd, sit. It's even, stand up. Alright, then we're back counting. You don't have to go in parallel, right? Don't go into already. Alright, ready, go. Okay. Suppose that we were to do this 10 more times. Who could tell me what the standing would be sitting? Right, this is an example I'm saying where I'm telling you basically I'll sit down now. And like that kind of question, how can we think about answering this sort of question, right? It's this massive variable system, these things going on here, just by some really simple rules. We can get this fairly complex behavior arising over time. It's really hard to predict, but actually the step. Okay? So thinking about this problem is thinking about sort of and they're often used as a framework for investigating these kinds of complex systems. So basically given some initial configuration of different parts and some kind of simple rules that describe how things change over time based on all the moving parts, then you can observe the behavior of that system and figure out things about it. This idea was kind of first conceived by John Conway in the 1940s toward making machines that could make themselves self-replicating machines. Okay, so in general space have some number of dimensions of cells. The cells just kind of replace them. There's a positive dimension, positive number of dimensions, and then some positive number of states that can be surrounding each cell. Okay, so you have a bunch of different states trying to replace them. And then you also have this set of rules describing how there's a change over time based on the behavior of our cells. And this is called collision-based computing, because it's kind of like physics, right? Look at how things are within an area, and I can enable to predict what's going to happen from there. So it's used for things like I mentioned, nature, like crystals or fluid flow, growth of seas, things like colonies. It's kind of these kinds of methods of parallel systems. And also, like what I was trying to do, you can think about making a machine makers or self-replicating machines, where, okay, you can build a machine, just a configuration of states, where you feed in something that specifies another machine, and then the output is a configuration of states that actually is the machine that you specify. Okay, so you're telling it about the machine and do it for you, and it just itself is another collection of states. So to give a demo of Randall's work, I'll switch over to this thing. This is Randall's universal constructor. So here's the machine, and now I'm going to paste down the instructions for building a copy of itself. That's what it looks like. as you run it, as I can see the tape going across the board on you. This is it reading the instructions, and here is this construction arm that's going to build the copy. Already you can see these three little dots right here, they're a little bit different colored. Three dark dots, that's corresponding to down here, the very base of the machine. So if we were willing to wait for a really long time, so eventually build a copy of this machine starting up here. So it works. We figured it out in builds using replicating machines in this case, but it's kind of complicated. You have to have 29 different possible states per cell. That's where all those different colors are represented. Yeah, it's complicated state transitions as well. So, sure, there was an easier way to do this kind of thing on Conway, and I did something he found that probably the name of life. So, John H. Conway, he was born in 1937 in Lincoln. So, actually, went for a bachelor's degree professor at Cambridge for his 12 years. In 1983, and then he became the Global Chair of Mathematics at Princeton in 1986. He likes all kinds of things, all kinds of interesting problems and games, big theories for numbers, not theory, game theory, theories, something we were talking about. As well as kinds of awards as well. He's a fellow almost in London. This is what somebody else described the process of human students making. After the rejection of many patterns, triangular lattices as well as square ones and many other laws of birth and death, including the introduction of 283 census, acres of square paper were covered. He and his admiring entourage of graduates took a shuffle paper chips, foreign coins, carry shots, ghost stones, or whatever came to hand. Until it was a viable balance between life and death. This is what they came up with. You have a world, only two dimensions, and each state can only have two different configurations. Either it's alive or something in that state or it's dead. And then the rules are also really simple. There's only four of them. So every step for every cell is going to look at the 8 angles around. So we've got a middle cell, we're going to look at the 8, maybe around it, and say, okay, if I have fewer than 2 papers, I'm going to buy if I have exactly 2 neighbors, then I'm going to stay there. I'm going to allow them to get over here. If there's 3, then those cells can be blue. So I've got myself, and if there are 3 around me, then it's going to come to life. Then if there are more than 3 around me, sorry, if there are 3 around me, then I'm going to come to life if I'm dead. And then if there are more than 3 around me, then I'm going to die because it's just those rules. Okay? So here's an example of how they work. We've got and neighbors of less than 2. Like here, we've got 1 with nobody around, or here, there's only 1 guy around. This one here, they die. Alright? If it's equal to 2, so this guy here has got these 2 as neighbors around him in a set of 8. So that means that he should stay. And that's true for all of them in this case, so they all stay in persistence. Here, reproduction, this guy says, okay, I'm going to look around for 2 here. Actually, I think this is a bug in my slides. But it's that was wrong. There are only 2 around this guy, so he should actually just persist. We can try this as an example later. Yes, it's this guy who's coming alive. Thank you. You're right. I was thinking it was that guy. Okay, and then overcrowding is the middle guy here who died because of the trick is that you don't have this variable which can use it. That's not persistence rule play. That's the one I'm doing there. Okay. Basically a fixed pattern. Okay. Some things persist over time, and that's the pattern makes the life. Oscillator is something that changes over time. As you step between these sequences, it can change between various unique states, but it's stable. We're always going to oscillate between these things. Spaceship is an oscillator that moves across space over time. So these ones here are called gliders. They can travel along the head like that. These ones are here we can see these gliders being created here. I'll talk about this thing in a second. But when three of them smack together, they actually turn into a live spaceship. And then that goes on further. Okay, gates are something that let you have some control over what's going on. Okay, so we've got this trajectory of spaceships, and now a gate is going to come in and smash into the spaceship. So there's a glider gun up here generating gliders, and we use it as a gate on this spaceship gun. So when they smack together, then they explode. So I'll show you how that works here. So right now, this guy here, he's going to open the gate. So we've got these gliders falling down this way, and spaceships being generated out here. And this guy, if I left him in, I'll open up the gate. Let me show you what it does first. Closed. So see, every single spaceship that gets generated down here is being run. Alright, now let's go back in time. We'll bring back, this is another spaceship. He's going to smack into one of these guys. Open the gate. Okay? So let's watch that. Creates so much chaos that he actually takes out, I think, 7 of these gliders. There. So now the gate's closing again. Let's give me enough time. So for the first 7 spaceships to this gate. Okay. Alright, so stability is another important property here. So when you build a complex machine with all these different simple blocks all over the place, it'd be nice if they didn't just explode as soon as you start to get done, right? So some certain patterns need to have stability, need to have extra things that might stop them from self-destructing. So an example of that is something called the Queen Bee. This is the next one I'm going to show you in a second. This is a Queen Bee. What it does, it travels in way one direction, it deposits a beehive, and it turns around and goes back the other way, and deposits a beehive, and it turns around. But at first lay down, it's still there, it explodes. Okay, so let's see. Okay, so this is the beehive right here. So over here, and I'm going to look at another beehive. There it is. So it's not there. So, constantly, no more beehive, right? So instead, can do to stabilize this is to put a couple of stable patterns on either side. Right? So let's see what happens. Now, blocks in here are responding to the rules, right? There are 3 around this guy, so it's going to come alive. So now, sometimes you need to be able to duplicate a signal. So a signal can be thought of as a glider or a string of gliders traveling across space. So sometimes you want to say, okay, give me 2 copies of this thing, how do we do that? Well, here's a gun. Looks like it's shooting gliders in this direction. And now here we have these queen bees that are kind of shuttling back and forth like we saw before. But when you arrange it in this particular way, you build something called a buckaroo, which basically takes a glider that turns it angles. So they're coming this way and then turn out going this way. Here, they've kind of put 2 buckaroos together in this particular way, so that when gliders come in, yes, this guy turns this way, but also a new one gets instantiated going this way. Only when there's somebody here. Otherwise, nothing comes out there and nothing comes out there. Okay? So that's how you can split a signal into 2 copies. Okay. Great digression of Turing machines. So Turing machine is this sort of computation construct that lets us think about things that can be possibly computed and be done. So it requires these things. We have a finite set of states. So you can see up here we've got 3 different possible states. transitioning between those states, and so what those arrows represent, it's kind of not like they're trying to set them, so you can see it. We have an infinite sequence of cells. Okay, so it extends over in both directions. We have a set of symbols that can describe the contents of each cell. So here it's just 0, it means two of those cells as well. And then we have to be able to read and write the symbol of the cell. That's what this is here. So this is like the read right here. You can see what's there right now. Put in a symbol there if I want to. Let's do. And then the machine has to be able to move. So this is the machine. That's the tape. It has to be able to move back and forth across. So the state transition then specifies these 5 different things. So it says, okay, here's the current state, and this is this. Once we know the current state and everything that we just read off of the tape, then we can say if that's true, if those things are that way, then we need to move to a different state, we need to write a different symbol into the cell, perhaps different, and then some direction for the machine to move from left to right. So it can move parallel, left to right, English terms there. So this is what I just said. We read the symbol from the current cell, so here we'd say, okay, from the 1, find the transition that matches both the current state and the symbol read. For example, second, we change to the specified state, write the new symbol that we're supposed to write, and then we wrote this machine symbol. So we have things over and over. The universal Turing machine now is this basically a Turing machine that can simulate the behavior of any other Turing machine. So you feed into it a specification of some Turing machine, some program or something you can pick up that way, and an input to that machine that you're telling it about. And then its output is the input that that machine told it about later generated. Okay? So it's kind of this super Turing machine that can do anything that any Turing machine given can do. Okay, so here's an example. This underline here that shows where the right head is right now. This is our tape. It's finite for the purposes of this example because my screen is finite. And okay, this is the state we're in right now. We're just starting. These things right here describe, okay, this is what we should write to the tape and where we should move as the machine. So right now when we start saying it says we should write a 0 and we should move 1 step to the right. Okay, so we wrote a 0 there, we moved 1 step to the right, so now we're looking at the 1. And we're in state 0 as a result of that transition. Oops. Okay, so we're going to now look at what's here, we find a 1. We're in state 0, okay, that means a 1 tells us that we're going to move to state 1 and we need to write down to 2 and move left. So we're going to write down to 2 here and move to the left. Okay, and then we're in state 1, and this process goes over and over again. The program that's encoded in this set of states is to duplicate any string of 1s that you give it return, to double it, to double its length. So we gave it a string of 2 1s at the beginning. So now it's just like here, it's round out. Okay. Okay, now to talk about Turing machine in life. This is a design by a guy named Conway. Okay, and really the ability to create a Turing machine in the game of life is understood by Conway shortly after he created the game itself. And no one had actually ever done it. Like they proved it theoretically, given certain properties of the game, but no one had yet figured out how to actually build something that could exhibit this behavior. So how would we pull this off? Like a set of states, transition rules, and tape, all these different things that make a Turing machine. We have to represent them in the game of life. So let's start with these states, transition rules, and then a set of symbols. Well, we can use these ones. We need some Turing machine to try to represent as a first pass. So let's think about using this particular Turing machine. Okay. So we have at least these states and transition rules for a Turing machine. State 0 and 2, symbol 0 and 2, the transition rules, where we can move, where we can write, and then what we can do is the machine. And so we haven't yet represented these things like where we are right now, it's just read, but we'll get to that in a second. Okay, so we want to be able to represent three states, three symbols, three directions, so we need those numbers of bits to represent these things. Okay, so we're going to create these bits using gate analysis. However, to make universal machine, this is what we're going in mind. He's building this thing. I'd like to extend this to universal machine eventually. To do that, you need a little bit more. You can have 4 bits for 16 states, 8 symbols, and 2 directions. Okay? So, yeah, he decided to use these things and continue to use things. It's also nice for us to think about because it turns out to be bits. So, how do we actually store transition points? We have to have a memory in the game file. Well, those buckaroos are useful because they can change the direction of the glider, right? And so if you put enough of them in the right places, you can loop the glider around and around and store information because you can loop a string of gliders. If a glider's there in the string of any gliders, that counts as a bit being turned on. If it's not there, that counts as a bit being turned off. Okay? So you can loop down here, so there are gliders that will travel around this loop here. And really, what's going on is that there's a fan out here. Okay, so a glider comes in and it says, okay, I'm going to both go this way and this way. So it duplicates on this side to send it around the loop again, and it also tries to escape, like the numbers here. But it's stopped by a gate, like we saw that gate before. It was blowing up the spaceships as they were trying to leave. That's what's happening here as well. So now, like we saw the gate opener as well, right? That spaceship that crashed into the thing that was making the gate run. It blew up the gate for a little while to let things escape. So that's how you can access the inputs and the contents of this segment. Okay? So let's see how that works. There it is. So right now, we're going to see a couple of gliders going around here. So there's one of them. And there's another one. You can see this guy, both he tries to escape and he gets reinstantiated over here. Okay, so they're going around and around forever. And this gate is stopping anyone who tries to escape. But we have now 2 spaceships that are going to come here. And this is an example of addressing a cell of memory. So if you have a grid of these things, you can say 1, 1, row, and then when they collide, they're going to turn into a glider. There it is. Now that comes down, and it's going to open up our gate to allow the memory to be read. So their numbers are down here. So these 2 guys are going to have a chance to go out, and if there are 8 of them, there would be time for all 8 of them to go out. And then, see, they're still here in the memory cell, we haven't lost them or anything. Right? Because we're sending out copies all the time. But now these copies are going to get going because the gate's supposed to go. Right? So I can see our memory, our information now is left the memory storage and connections. So yeah, the row selectors and the column selectors, that will let us address an array of these things. So we can say, alright, if your state is state number 1, let's say, the symbol in red is, I guess, state number 1 here, and if the symbol was 0, then we'd send a guy along here, and a guy along here, and they'd smash here, and then we'd read from this particular symbol. Yeah, and so we're using the current state and symbol to index the appropriate cell. This is how they're arranged. Okay? So this is saying, alright, we saw symbol 1 on the tape and we're in state 0. And so now, this tells us our information basically in binary, these x's are not 1s, about what we should do. 0 means that the machine should go left. This means that we should write a 2 onto the tape. Right? Because it's a binary 2 just there. And here, this means that we should switch to cell number 1. So this is the encoding of the instructions of that particular piece of memory. So that's what's living in this set, is that string of 8 vectors, represented by 2 gliders bouncing around. Okay? And so we can see that replicated here. If we're in state 0, and we saw 1, there's a 1, then we need to move to the left, that's that 0 here. We need to write down a 2, that's what this is here, binary 2. And we also need to move to state 1, which is what's down this way. So this is a representation of this state machine now in this kind of grid structure. And all the states and this combination of states and possible symbols you can read using states 9 gives a label that you have to represent. Okay, so that's we represented these things as states, transition rules, and possible symbols that can be on the table. But now we need to take and the ability to drag it on both of those axes as well. So if you have two stacks, you click them at each other, so the tops of the stacks are facing each other, you can able to tape. Right? To move the machine, you effectively pop one stack and push the other. Like this. So if we want the machine to go to the right, then we can pop the stack on the right and push the stack on the left. So we can go back and forth. There are 8 symbols, so we need to have a stack where each piece of the stack involves 3 bits to represent your possible symbol in the stack. So bits are represented as trapped gliders. So these black lines here are showing our fingers of fan. So a glider is going to come along here and turn this way, and another glider is going to come along here and turn this way. So there's this interaction between gliders, and you have them kind of one stream going in one direction, one stream going anti-parallel to that. Then any glider in between that's going in this direction will bounce between them and just stay there. It can't go anywhere, it just bounces back and forth forever. And so that way you can keep a piece of information trapped in the system over time. And so pushing and popping then will involve making holes in these walls so that the information that's inside them can travel on to the next trip, right? So right now, if these walls are in place and we're not trying to push or pop, those bits are trapped there forever. But if we make a hole, then they can travel through and end up down here, which is like we're pushing something down further into the stack. Okay, I'm going to show you this in a second. So that's all the pieces. How does it all connect, though? Well, this is the diagram. See, so we've got 2 stacks on either side, so kind of the symbol we're dealing with is going to be here, the read write head is going to be here. So we have a finite state machine that I showed you that created different cells. So the control flow is going to work like, okay, we know what we're supposed to do from the memory cell, we know if we're supposed to move right back, send that to right, what state machine and then next. So this thing's going to split that all up into its different pieces. It's going to send the state transition around this way. It's going to say, okay, do we have a symbol to push? Yeah. We want to write something and then we have to learn, so we're going to push eventually. So all of that comes with stack control. It controls, okay, should we be pushing or popping from each stack to move in a particular direction? And the symbol that's being read right now will come up down here and be used to select what state path will be next. Because we need to know our current state and the symbol that's being read. That's what it looks like. And here's how it runs. So you can see right from the get-go, we have some information stored. These are our layers of our stack on one side. So you see this little guy right here? That is representing a 1 to the right of the read write head. Okay, this guy is just bouncing back and forth forever. Even though it looks like there's holes here, they're never in the right place for him to escape through. Okay, so there's a 1 there. There's also a 1 down here. So this is the initial configuration of the example I showed you, right? You have a set of 2 1s. We're going to try to duplicate and set double the length of that set of 2 1s. That's what this machine is trying to do. So it all starts with this guy. If I were to delete these pieces, which I'll show you here, then the machine is never going to get its start signal. So I'm going to zoom forward in time here. Kind of see that, yep, those guys are still trapped there. We're going, what, 20,000 generations into the future, still nothing interesting is happening. Okay, this is the kind of steady state of the machine. That's not been told to start yet. All right, so I'm going to stop, scroll back. Okay, and I need to undo to bring back the guy. There he is. Okay, so now let's watch where he goes. So he's going to sneak past them. And maybe increase time a little bit. Yeah, okay, that's good. So this is kind of the main control sequence for getting into the stack. So right now he's going to smack into there and he's going to make a hole in that. That's often how information sort of changes hands in the system, that a 1 surrounded by zeros becomes a 0 surrounded by 1s. You invert the sequence. That's kind of necessary for making these turns in some cases. And so now we've got this hole that we're watching. It's going to come into this control system and split up in various ways. This is the thing that's saying, okay, we need to do a bunch of stuff now, right? The first instruction from our state machine, I don't know why that went back there. Where is it? Here. Right, so right now we're at start and we're saying, okay, right is 0 and move to the right. So a right, moving to the right, that's represented by a single 1, and writing 0, that's represented by all zeros. So all we should expect to see is a single glider, and that's what that one glider represents. This is saying that we're going to write a 0 and we're going to move. So how do I get back? Yeah. Speed it up a little bit. All right, first thing that's going to happen, there's a fan out here. So this hole is going to get replicated on both sides. So he goes through here, and now there's a hole up here as well. The hole here is going to let one of these guys escape. All right, he's going to bounce around. This is one of those buckaroos. He just changed his direction. Actually, it's a fan out as well, so now there's a new information up here, so they split that signal up there. But let's just follow this one guy for now. Whoa, where'd he go? Yeah, okay. I sped up the simulation accidentally. I can get back to it really quickly though. Okay, there he is. The hole's going up through here. Right there, that's the one I want to follow. Okay, so that is showing, this is the state transition information that we should end up in this particular state. And I think it's also still encoding that we wanted to do a write or something. So there's a couple holes here, but this is going to clean that up and give us only the information that we want to switch to state 0. There it is. So it's being delayed by this long loop because other stuff has to happen before we switch, right? It has to be synchronized properly. Okay, so it's going to bounce down here now. And here we're getting toward our memory addresses, right? And so here, our selectors are going through, right? There's the gap. There's a single guy going down again. Okay, I'm going to slow down now. Right. He's going to smack into here and disrupt this particular glider gun, making a hole. Here is a spaceship gun shooting spaceships going up. Okay, so this spaceship is going to break there. So we've got a hole here now, and that's going to let one of these spaceships go through. There it is. Okay. And now this guy is going to smash into these different guns up here. And the whole purpose of this element is to basically break up this signal of which state we want to select or which state we want to end up in to read from so that we can generate a spaceship flying across at the right level. And so we'll see that happen in a second. I believe it should be around here somewhere. Where is it? Oh, I missed it. There it is. See, and there was that reaction I showed you before, where two spaceships collided to make a glider to now read from this cell. And see these 8 guys going across here? They're going to carry the information from this memory cell over to these guys. Because these gliders are going to come out on a diagonal. If we just let them fly, they'd crash into this thing and blow it up, right? And so we're now reading this piece of memory here, which is telling us everything we need to know. Okay, look at this pattern here. We've got 3 things on, and off, and on, and off, and then 2 on. So 3, 1, and 2 with blocks in between. If I go back over here, 3, 1, 3 zeros, 1 0, and 2 zeros. It's the same pattern. Okay, so that's the information. We're being told that we should move to this particular state 1, write a 2, and move to the left. That's the information coming out of the cell. And this one. Okay, so there it is. Okay, so there, we've just inverted the information that's flying up. There it is again, right? We're back to where we started. This is where we initially sent that control signal about what we should do. Okay, that was the first transition to state 0 and step back to. Now we've got more information coming in, which tells us to go to the next thing. If we look over here, things have been happening in the meantime. Remember how there used to be 2 gliders bouncing around between these 2 things over here. And now there's only 1 glider, just this guy. There's nothing over here. That's because we've done that. We've moved the read right hand as opposed to the right. So 2 blocks to where it was before, we moved the right one, and then we moved only 1 left to where it was. That's what we're seeing now. Okay. So that's an example of reading part of the information kind of flying around here. I'm going to go back in time now to show you when these state transitions, or the stack operations. So that's kind of the last piece of understanding what's going on here with this. So, back at the beginning with this super guide. And so it's just that one guy that has all of this effect because he gets split up so many times. So that was the one we followed before. But really, there's this one too. And there are these guys as well. Maybe that was the interesting. Alright, let's watch down here and see if we can watch where that gap is going to open up. So for this guy to escape, or for information to leave this area, we need to have something happen to this glider stream. So if you look back over here and expect something to smash over there. This guy's doing something on his own. At the same time, so after this guy goes, we're going to need to have this guy transition. To move the stack onto where we need to have the bits go up and down in the stack. So I'm just going to zoom forward to the point where we actually saw it. Here we go. See what we go? Way bigger than it was over here before, but this guy could never escape through. Escaping into freedom. This is the one that was on our stack. Yeah, the guy here from here is gone. He's also not here yet because he's in transit going through here. He's bouncing around. This is him, I think. Yeah. This guy, he's being delayed in here to make eventually he's going to be able to squeeze through one of these holes and get trapped. There we go. So that was the clock direction. Now I'm going to speed up a little bit. Right, we were writing 2s at one point going through that Turing machine, so we shouldn't see bits kind of along here instead. Skip into time. So it takes a few cycles to have interesting things happen. Yeah, so there's a 2 now. There's down here before. It's gone, it's back to 1. So if you kind of see spread out over all these systems, all these different stack operations. There are the 2 2s and that's. Let's pick that whole lot. We should ultimately end up with 4 1s, right? Because we're still with 2 1s that are driving programs that duplicate them. You can see the end of the red down there. Close now. We should see what it reads because the machine should have loaded. That's like that. So there's a little bit on. Yeah, completely stable configuration. The machine is open, it's done what it's supposed to do. So we've got a run here, a run here, a run here. So there's the here, and yours over there. So that was the machine, and we execute its operation. We got all up to connections, like 200,000 connections. Okay. Sum up a little bit. So if you're kind of figuring this is the basic level, it's really, really simple. It's just if your name was changed, do something. Probably changed. Okay. But at the higher level, we have a Turing machine that can make kind of the Turing machine can make a decision instead of going to talk about this particular level, we can do that too. And so if we could build this universal Turing machine in the cellular time, we could feed the Turing machine itself and not have to have the Turing machine represented in the states. But at least the state traditions represented there, they can not have that program. We could feed that into this thing as well. And so it's been done. Oops. This is at this first design was that if I had this little things coming down to our machine. It's easy, but it's still really hard to use. And so we kept working. What I showed you was from about 2001. This is what he made, I think, about 3 years ago. Looks a little different, but really, it's the same. This has an infinite tape. Sure. That's these guys. So I'm going to switch now to those to the simulator. Hash life was much, much faster. So we can actually see what happens. This is what would happen for the things at regular speed. This is as fast as this computer can read at the moment. Okay, so we're seeing things chugging along. It would take a long time to see anything that comes to that. So machine can do it. not sure if it actually happens or if it's giving you some overall system kind of life scenario, which is pretty powerful. So like a fair number of parallel things happening at the same time. Just the take over. Yeah, so I was like redesigning some of the pieces that I showed before, which that's really big, but also the configuration of things work is different just to support this automatic learning process. So you can actually create multiple code. And so the problem is always think about what's going to happen with this millions of generations later, because it actually does need to simulate the projects. So, yeah, choosing the uses of rules can be kind of tricky as well. So you don't have sales on time can be tricky as well. So that's pretty nice that you can look at these things and lots of parallels and see the big picture and zooming out further and further and observing these interactions and then kind of diving into whatever seems to be of interest. So that's the talk. This is our chapter book Computation computing. And we'll about his first machine. You can check that out so you can research it from there. And also you can find out full details about how this thing works on his website. Further reading, you can see about members of the instructor. So Tom Conway and lots of good relations. And that's all I have to say. Thanks. So, what do you think? Yeah, so this particular thing. Yeah, I don't know if this particular machine, it's like this particular implementation that's been proven to be a universal machine. It's been proven that it's possible in game of life anyway. So it's not as though they're kind of, they have to defend because it just can't be done. So it seems so far like to me it looks like the team is being creative and further what was supposed to do. The rest, like being able to have this control object and store memory, like it demonstrated